Okay, so this is section 15.2, video number 3. We've been doing iterated integrals. We're just going to keep on going with example number 7. We've only got 3 examples to go. This one's pretty short overall. So a couple things about notation. That little r down there in the bottom means that I'm taking the double integral over the set of real numbers, but they are giving us the actual bounds right here. So x is going to go from 0 to 1, y is going to go from 0 to 1. In this case, it doesn't really matter because they're both 0 to 1. Typically, it would be x first, then y, if they don't specify it. Usually, it will be specified, but this is going to be your x bounds. This will be your y bounds. So let's go ahead and write it up. Now, does Fubini's theorem apply here? It sure does, because I can separate these things. So I'm going to have the integral from 0 to 1 of 1 plus x squared dx times the integral from 0 to 1 of 1 over 1 plus y squared dy. Algebraically, they are separated. So just because it said that it has to be things that you could write as products or things that are being multiplied, I mean, technically that's still the case. Even though it looked more like division, they're still technically being multiplied together, so we could separate them. So let's go ahead and figure it out. Antiderivative of 1 plus x squared is going to be x plus 1/3 x cubed from 0 to 1 times. Got to remember this one, throw back a little bit. The antiderivative of 1 over 1 plus y squared is an inverse tangent. So that'll be the inverse tangent of y from 0 to 1. So let's see what we get. Plugging in a 1 for the x's, we get 1 plus 1/3 minus 0. All right, so we're going to get the inverse tangent of 1 minus the inverse tangent of 0. So now we have to remember all of our values. So on the left side, we get 1 plus 1/3, which is 4/3. Let's see, inverse tangent of 1. Tangent of what angle gives us 1? That's going to be pi/4. An inverse tangent of 0. Tangent of what angle gives you 0? So that's 0. So we ultimately end up with 4/3 times pi/4, which is going to be pi/3. And that's it. So whatever that curve, 1 plus x squared over 1 plus y squared looks like, the volume underneath of there would be pi/3. Okay, not too difficult. Just kind of wanted to reintroduce the inverse tangent one there, I think. All right, this one will take a little bit longer to do. So I've got the function x square root of x squared plus y. The bounds are constant. The question is, can this be separated? And the answer to that is no. I cannot separate out that y from underneath of the root with the x squared. So we can't use Fubini's theorem. So we do need to set up the integrals. The integrals are going to go from 0 to 1, 0 to 1, because they both happen to be that way. The real question is, what comes first? Am I going to do dx first, or am I going to do dy first? Well, considering the only way to do this one is going to be using a u substitution, and when I use a u substitution, I want to get rid of that x on the outside. So think of this like it was a u substitution that you would have done in like Calc ABBC, where the x squared would be underneath the root would be like x squared plus 2 or something like that. Then you would let u equal x squared plus 2, and it would get rid of that x on the outside. Same idea. So we really want to do this with respect to x first, and then y. You wouldn't want to try and do an antiderivative of this thing with respect to y first, because a u substitution just isn't going to be helpful there. So let's go ahead and do our u substitution. So u here is going to be the composited piece, x squared plus y. Remember, we're taking this with respect to x. So it'll be 2x dx. Oops. It'll be 2x when we multiply the dx over. It'll be 2x dx. And then solving for dx, we get du over 2x. Okay, so let's go ahead and write this up. So I'm going to go ahead and change the bounds. So if I plug 0 into my x, I'm just going to end up with y. If I plug 1 into my x, I'm going to end up with 1 plus y. I am now going to have the integral of x square root of u times my new dx, which is du over 2x. Don't forget we still have the dy. And the good thing is the x's are going to go away. We needed that to happen. I can pull that 1/2 all the way out to the front. So let's do that. And then we're going to take the antiderivative of u to the 1/2 du and then dy. And again, we cannot go ahead and use Fubini's theorem from here either. And a lot of people try to do that because they're like, oh, now I can separate the variables. The bounds are not constant. Can't do it. So just take the antiderivative with respect to u first. So that's going to be u to the 3/2 times 2/3. And we're going to evaluate that from y to 1 plus y. Don't forget the dy on the outside and all the other pieces. I'm going to go ahead and pull that 2/3 out to the front. So that's going to end up giving us a 1/3 out in the front. Plugging in the 1 plus y, you're going to get 1 plus y to the 3/2 minus y to the 3/2 dy. Okay, and this is going to be very much like the problem before. I don't need to do another u substitution here. So I'm just going to take the antiderivative of the 1 plus y, because it's really just a quantity of a linear function with a slope of 1. So just call it like u if you want to, u to the 3/2 or something, but you don't have to write that whole process out. So this will just be 1 plus y to the 5/2, and then dividing by 5/2 is multiplying by 2/5. Same thing over here. This will be 2/5 y to the 5/2, and we'll be evaluating that from 0 to 1. Don't forget your extra 1/3 out in the front. Again, so I'm going to go ahead and pull the 2/5 out to the front. So that's going to give us 2/15. And then plugging the 1 in, we're going to get a 1 plus 1 to the 5/2, or 2 to the 5/2 power, minus 1 to the 5/2 power, which is just 1. And plugging 0 in is going to give me 1 to the 5/2 power, so that's just 1, and then nothing. So it looks like we're going to get 2/15 2 to the 5/2 minus 2. Right, -1 minus 1, yeah, minus 2. So I think that that looks okay, and there's absolutely nothing wrong with this. Just so that you can see, like if you were to look this up in the book, believe it or not, the book would not have it written this way. They go much further. Not really sure why they feel the need to, but they do. You could factor out a 2. So we could factor a 2 out of that. If I factor a 2 out of that, well, factoring a 2 out of that is going to multiply a 2 on the outside. So that's going to give me 4/15. And then let's see, factoring a 2 out is going to give you 2 to the 3/2 minus 1. No idea why you would really want to do that, but you could. You could also rewrite the 2 to the 3/2 in terms of roots if you wanted to. So it'd be 4/15. What is that going to be? The square root of 2, square root of 8. So that's going to be 2 root 2 minus 1. And believe it or not, again, if you look it up in the book, I believe this last one is the way the book actually has it written. There's really no reason to do it. Any one of these are perfectly acceptable. These are all acceptable forms. I would probably just stop at the first one, to be completely honest with you. But I just wanted to let you know, if you were to try and look something like that up in the book or whatever, what it might look like. So, all right, let's go on to the last problem. This one says, sketch the solid that's defined by this particular integral, double integral. All right, so if we want to sketch the solid, the first thing you want to look at is, what is your domain? basically, what is the domain of the projection down into the xy plane? Well, x and y both go from 0 to 1. So really, x is going to vary from 0 to 1. Y is going to vary from 0 to 1. So there's your domain. So if I kind of want to sketch this thing, I know that at least the base of my domain is going to go from 0 to 1, 0 to 1. So looks something like this. That square region right there, that's going to be your domain. And then what you want to do is you kind of want to figure out what the z values are at the corners. So let's write that up. We want to find the z values at the corners. Okay, and that may not always tell us everything, but in this case, 1 plus x squared plus y squared, this won't be too difficult to figure out because there's not going to be a lot of massive changing in the first quadrant from 0 to 1, 0 to 1. So let's go ahead and figure some things out. So when, I don't know, x and y equals 0, let's do that corner first. So when x equals y equals 0, so now we're talking about basically on the z-axis. What's the z value? Well, the z value is 1. So let's plot a point. Maybe right there. I'll try and do this in different colors to make it look a little easier. What about when x equals 1 and y equals 0? When x equals 1 and y equals 0. If we plug those back into this function, we're plugging everything in here because that's our z function. If x equals 1, you get 1 plus 1 plus 0, so you get 2. So z is going to be 2. So when x equals 1, y equals 0, you're going to get 2. So that would be, maybe if we went out this way, that would be like right there. Not really drawn to scale, but you get the general gist here. That's going to be 1. Let's do one of these in blue. So let's do another corner. When x equals 0 and y equals 1, z is also going to be 2. So about the same height right there. And then we've also got when x and y both equal 1. So let me do that one in, I don't really have another color to choose from that's going to work really nicely here. Guess I could use red. When x equals 1, y equals 1, z is then going to be 1 plus 1 plus 1 is 3. That's going to be much higher. It's going to be like way up here. So something like that. And then if you were to connect these things, it looks like it's going to bend up like this, bend up like that. And again, this is why I said this is hard to do. It's then going to kind of bend up into that one and then bend up into that one right there. So obviously the difficulty there is the depth. If you can see this really well, then you're doing great. It is hard to see. But ultimately, what you want to know is that last point, this one right here, that's the one that's closest to us. That red is the one that's closest to us. It's really hard to show the depth. If you're good at shading, you might be able to do it. Instead of that, I am not very good at showing that stuff. So what I'm going to do is I'm actually going to show this to you guys on a thing called Calc Plot 3D. I'm going to end up using this Calc Plot 3D quite a bit during these last 2 chapters. All right, so here is our Calc Plot 3D. What you are looking at there is the XY plane. So you're looking at it basically as much as I could go straight down onto the XY plane, looking straight down on the Z-axis. This is the corner. This is the lower one. This is where X and Y were 0 and Z was 1. And then it starts to come up, and then it starts to come up. This is where the Z value is 2, and then way up here is where the Z value is 3. Not easy to see from this form, but when I go ahead and scroll, Here we go. I'm going to go ahead and turn this thing. There we go. Now you can kind of start to see the depth. There, I'm trying to get it so it's in between where we were. Kind of right about there, maybe. Something like that. You can kind of see how here's where it is on the z-axis, and then it comes up all the way up to 3. These values out here were 2. So this is what it looks like. And then what we would actually be finding if you took the integral of that whole thing is the volume that would be projected down onto the xy plane. So hopefully you can see kind of what that looks like. Again, it's not the easiest thing to show, but there you go. So that should be enough for video 3. And yeah, that's it.